Okay, so we're for the next talk, we're delighted to have David Zuckerman here from UT Austin. So David is well known for lots of work, but especially in the complexity of randomized computation and de-randomization and the explicit constructions of various combinatorial objects, especially extractors and expanders and related things. He is not generally someone who writes a lot of papers that appear at crypto and crypto venues, but he is someone whose work gets used by people a lot, by people who write papers at these venues. I think almost all of us probably have done so. I've certainly cited and used his work many times. So yeah, we're really lucky to have him. And with that, I will hand over to him.
Thanks, Adam. Okay, so yeah, I want to tell you about work in randomness extraction that is relevant for cryptography. I'll talk about both old and new work and different connections between the papers. Okay, thanks a lot. That was exciting. Okay. All right, so as you know, so I won't go into why randomness is useful. We've seen that, and you all know that. You also know a bit about weak random sources, but I'll say a few words. I mean, some of the introduction has overlap with Yevgeny's talk, but I'll just go through it. So one motivation for weak random sources is that natural sources of randomness may be defective. Another motivation that's useful for this audience is that weak sources arise naturally in cryptography. If you condition on an adversary's information, then what was formerly uniform is now defective. They also arise in pseudorandom generators. Here you condition on the state of the computation. So the most natural goal is, if you have a weak source, you want to purify it, make it uniform. Okay, so first, how do we model a weak source? Okay, you're familiar with this, but let me just go through. If you're not familiar with it, you might first think, let's use Shannon entropy. A lower bound on Shannon entropy should be good enough. The problem is that you could have a distribution with, say, with probability 0.99 gives a useless string like the all zero string, with probability 0.01 is uniform. So this is useless with probability 0.99, but the entropy is 0.01 n. So typically we want a low probability of error. So this is not really the right measure. You might first think, well, let's just repeat it many times. But here, X is supposed to capture all the random bits you're going to use throughout the computation. If you're going to do some repetition, you want to already, then X should be divided into blocks, incorporating that repetition. Okay, so really the right notion is min entropy that I'm sure you're all familiar with. Take the largest probability, it's reciprocal in the log of that. So the min entropy of this particular distribution is just a constant, so we don't expect it to be useful. So we'll call a distribution an nk source if it's a source of n bits with min entropy at least k. In particular, all strings have probability at most 2 to the minus k. A special case of this is the uniform distribution on a set of size 2 to the k. And actually, there's no loss of generality in looking at such sources. In fact, any distribution with min entropy k is a convex combination of such so-called flat sources. Okay, so randomness extractors. So here, as Yevgeny laid this out as well, the ultimate goal would be just to have a deterministic algorithm to extract uniform random bits from any nk source. Right, so we start with this distribution, and let's just try to get out one uniform bit. And as Yevgeny explained, this is impossible, and the proof is simple, as Yevgeny showed. You look at the strings that map to 0, you look at the strings that map to 1 of this purported extractor. One of these sets has size at least 2 to the n minus 1. So the pre-image of 0, say, has min entropy n minus 1, but the extractor always outputs 0, and hence it fails. Okay, so clearly, so that's no good. So there are several ways to circumvent this impossibility result. So I'm going to say I'm going to do it somewhat differently than Yevgeny, but one is to make assumptions on the weak source. So you could define various notions either from an algebraic perspective or from a complexity theoretic perspective, and they both give interesting models, and this is useful. But if you don't want to make assumptions on the weak source, well, one thing you could do is use seeded extractors. Here, I wrote you want to extract using a short random seed. In cryptography, you often don't care about short, but anyway, you have a seed either short or long. And this has had many applications. Another is to extract using at least two independent sources. I should say some of these categories can sort of be combined in other ways, but I think it's sort of this is a clean perspective anyway. So here and here there were some dramatic recent advances, or if recent goes up to maybe 6 years or something. But anyway, so in this talk, I'm gonna actually talk about several different types of extractors. We'll see different interesting connections between them and uses in cryptography. Okay, so the outline, well, introduction. So first I'll talk about seeded and non-malleable extractors. We'll see how this is useful in privacy amplification. Then we'll discuss two-source extractors. I'll give some crypto motivation, and I'll sketch the construction. And then we'll see a bottleneck, because really in cryptography, we're going to want negligible error, but these constructions don't achieve that. And then we're going to see some ways to circumvent that, and some other extractors. That's more recent work. That I'll explain when we get to it. Okay. All right, so let's get started. So most of you are familiar with the seeded extractor that I just said. So here you can, right, so here you have your weak source. You add a small or large amount of extra auxiliary randomness, and then you can extract out a long string. So this is an extractor. Typically, we talk about strong extractors. So a strong extractor means that even if you see the seed, the output is close to uniform. So, or equivalently, the ordered pair, the output and the seed is close to the uniform distribution. So this is useful in privacy amplification. Evgeny said basically this, right? So you let's say Alice and Bob have a shared secret key, but it's not uniform. There's just some, it just has some entropy. And from then on, they're only allowed to talk through a public channel. So the goal is to convert this weak shared secret X to a uniform secret. And let's start out, we have an unbounded passive adversary. In this case, a strong extractor immediately gives us a way to solve this. So we pick a uniformly random seed. So let's say Alice picks a uniformly random seed, sends it to Bob, and the shared secret is just the extractor output. And remember, a strong extractor has the property that even given the seed, the extractor output looks uniform. So it's correct just basically by definition. This was even done before extractors were defined. They used a variant of the leftover hash number. So now what about an active adversary? An active adversary can arbitrarily insert, delete, modify, reorder messages, can run several rounds with one party before resuming execution with another, all sorts of things. Evgeny and Daniel, in order to handle this, Evgeny and Daniel defined a non-malleable extractor. So to see what this is, let's start with a strong extractor. So the definition is even stronger. So it's a non-malleable extractor if for an arbitrary adversary, tampering function A that doesn't have any fixed points. So it maps seeds to seeds where the new seed is different than the old seed. And the definition is that if you look at the non-malleable extractor output, even if the adversary knows not only the seed, but the output of the extractor on an arbitrary related seed, it's still the output is close to uniform. Okay, so it's a strong definition there, and so just as a trivial observation to help understand it, non-malleable extractor can't even ignore one bit of the seed, because then if it did, then the adversary could just flip that bit, and that would be the Y prime, and then the output would be determined just from this other output here. So somehow the different seeds have to give very different outputs.
So non-normal extractor, why the U is kind of uniform also. So Y is uniform and then U is so U and Y are so both uniform.
That's right. Yeah. Right. Those are both. Yeah. Both uniform. Any other questions? Okay, so Evgeny and Daniel gave a non-trivial protocol showing privacy amplification with an active adversary in just 2 rounds with near optimal entropy loss. Unfortunately, they didn't give an explicit construction, but since then there's been a sequence of works giving explicit construction. This was sort of the main. This gave, earlier we had a long seed, and then for large min entropy, and Chattopadhyay, Goyal, and Lee got it down to polylog n. And so the record is here. Now we're able to have a non-malleable extractor with seed close to logarithmic length and min entropy close to log also, and linear output. And we're going to see that this is going to become useful soon. Okay, so now I'm going to talk a little bit about multi-source extractors. Before defining, well, let me just say that a multi-source extractor is an extractor for independent NK sources. I'll define it a little more carefully in a minute. Let me first give some crypto motivation for this. This is called network extractor protocols. So here you have a bunch of parties that want to execute some distributed protocol. So the input, they have, the problem is that their inputs are not uniformly random, but they're from weak random sources, and let's assume that they're independent. So they interact with point-to-point communication, and then the goal is to output private, nearly uniform random strings, at least for the honest parties, because we're going to allow Byzantine faults, so the adversary can send arbitrary messages. Okay, so in other words, the players start with low quality randomness. They want to interact and end up with high quality private randomness. And so then after running this, you can run standard protocols like for Byzantine agreements. So a naive idea would be to design such extractors would be a few players could broadcast their sources, and then the remaining players could apply some sort of multi-source extractor to those sources and their own source. So this is kind of some intuition how it might be relevant. This doesn't quite work because maybe only malicious players broadcast. But in joint work with Yael, Shin, Anoop Rao, and Shin gave the best result that basically if the min entropy is just polylog n, you can still tolerate a linear number of faults in Byzantine agreement and in leader election, and with good constants too. Oh. Yeah, that's a good question. They do, right?
Yeah.
So I guess
It's a standard model of multi-party, but
I'll ask
oh.
to repeat relevant questions.
All right. So Ron asked about rushing, and yes, rushing is allowed in this model. Okay. So there was also work in the computational setting. Here you under some crypto assumptions, but this conference is about information theoretic results. So the high level point is that good multi-source extractors give good network extractors. And so that's some motivation. So let's take a look at these multi-source extractors, in particular a two-source extractor. Okay, so here we have two independent NK sources, and we'd like to extract, for now, let's just look at extracting one uniform bit. So this is the simplest setting. So more formally, for any NK sources X and Y, we want the probability that the extractor output is 1 should be close to 1/2. So it's helpful to think of it in matrix terms too. So here we let capital letters denote 2 to the small letter. And our goal here is to construct a big N by big N matrix such that every big K by big K submatrix contains about the same number of zeros and ones. So to see why this corresponds to a two-source extractor, you could think of the one source as picking a row. So we could think of it as a flat distribution. It just picks one of these capital K. It picks a set of capital K rows and picks one of those rows uniformly at random. Similarly, the second source picks a different set, perhaps different set of size capital K, and a random one of those columns. And then if the matrix is labeled by the extractor output, the output of the extractor will just be a random element of this submatrix, of this K by K submatrix. And since we want that to be close to uniform, it should be about half zeros and half ones. So that's the matrix view. Existentially, it's not hard to show using the probabilistic method that it suffices to have big K about log of big N. And that corresponds to little k also being about log of little n. So the question is, what can you do explicitly? So in a graph theoretic view, it's so here I'm just viewing that matrix as a bipartite graph. I'll color edges green if they're 1 and if the output is 1, and red if the output is 0. And so it's just saying, if you pick any set of size big K on the left, any set of size big K on the right, there should be about half green edges and half red edges between them. And if you're familiar with Ramsey graphs, this is a stronger definition than a bipartite Ramsey graph. So it's very interesting in that context. That was a major application of this, but since this is a crypto talk, I won't go into that. Okay, so you might be thinking, well, how hard could this be? I'll just write down some reasonably random looking matrices and that should work. So here's one attempt, right? It's natural to try just taking the inner product mod 2. This has some nice properties. It gives a Hadamard matrix. In particular, if you start looking at eigenvalues, you see that basically all non-trivial eigenvalues are square root n. And this is the smallest possible second eigenvalue. And then you could apply the expander mixing lemma to this. The issue is that the expander mixing lemma only gives a good bound on the number of edges when the product of S times T is bigger than N. So it gives an extractor from min entropy bigger than N over 2, but it doesn't do better. And this is a problem. This is a big bottleneck. It's hard to beat the expander mixing lemma. It's a very powerful lemma, but it's good to know also that the expander mixing lemma it's good for large sets, but it's not good for small sets. Right, so eigenvalues can't give a better extractor. This is an issue before. And so one way to view this is, can we beat the expander mixing lemma for small sets? Okay, so can we get an explicit construction? So Shor and Goldreich, define basically this model building on a model by Sant and Bazzarani, and they essentially asked for an explicit two-source extractor. And again, the probabilistic method gives tiny k, just logarithmic, but it was very hard to beat n over 2. So basically getting n over 2 is essentially what I just said. Bourgain was the first to beat n over 2 for both sources, and he only did it a little bit. I think 0.49n is, I think, even giving him more credit than God. And then, Ron Raz showed how you could have one of the sources be very small. Actually, for 1 bit output, this was folklore, and he showed how to get many bits. So given the difficulty there, people looked at C-source extractors for some small constant C. And here there was some very nice work getting linear entropy. Rao got it down to just min entropy n to the gamma for any constant gamma. And then Shinli got it down just to 3 sources, min entropy polylog n, and really small error. So this is great, but again, 2 sources was
So for these for multi-source extractors, is it the case that sort of once you can extract a bunch of bits, you can extract sort of all the randomness, or is there also are there interesting gaps between?
Right. So
how much they get.
Okay. Yeah. So Adam's asking about extracting more than 1 bit. Yeah. So there. Right, we'll see that our construction just extracted 1 bit, and then Shinli showed how to extract many bits. And typically you can get out more bits, but I don't know if there's. I'm not sure there's a theorem, right? I don't know if there's a theorem that says any 1 bit extractor implies. Yeah.
Yeah, that's what I was asking. There's some generic thing where if it's like for every construction, you have to ask, okay, and also how many bits.
Right. So I don't know of any generic way to improve the number of output bits. So a few years ago, Ishan and I gave the first 2-source extractor where we got down to polylog n bits, which was nice. The downside of our construction was that the running time was polynomial in n over epsilon, where epsilon is the error. And of course, in cryptography, we want negligible error, so the running time would be super polynomial. And so I'll discuss this bottleneck in a bit. But first, I want to give a flavor of our construction, and then we'll see what the issues are. All right. So since our work, there were improvements. Like I said, Shinli got out many bits, and then this constant C got very small due to a clever idea by Benaroya, Duron, and Tashma, and then it got all the way down to log n. Actually, you can even Shinli then later was able to divide this by triple log n, but it didn't fit so cleanly in this slide. So.
Did Cohen do anything about it? Or?
Sorry?
Asking Gil Cohen did anything about it?
Oh, yeah. Right. So, right. I mean, Gil also had participated in that as well. Yeah.
Okay. So before we question our assumptions, it's easier to get instructions.
Yeah. So there's been work along those lines. So the question is about if you have crypto assumptions, what can you do? Yeah. So we don't know. De-randomization assumption. Yeah, I don't know of any de-randomization assumption that would give it. I mean, except for just assuming it directly. But that's a good question. Okay, so let's get a sense of a flavor of the construction. So the construction uses these extractors that I discussed earlier. Okay, so a different way to, so you know what a strong seated extractor is. Just a different way to view it is that you could cycle over all seeds, and then we end up with the seed length is little d, so we end up with 2 to the little d, which we'll call capital D functions, one for each seed, such that for any weak source x, most of the Fy of X are uniform. Of course, for different X, different of the Fy of X's will be uniform, but it's this view that will be helpful to us. Yeah, so this. Another ingredient is a resilient function. So a resilient function has a crypto flavor. It's so it's a Boolean function. And yeah, before I say the definition, let me say words. So here, think of n players that get together. They want to flip a fair coin. And the way they're going to do this is they're each going to flip a bit and then announce it. And then at the end, apply some Boolean function f to these bits. And we'd like these bits to be uniform. And the question is, what function f should you apply? And we'll allow rushing. That is, the bad players can wait to see what the good players do before acting. So that's exactly the definition here. So it's resilient for sets of size q and error epsilon if for any subset of q coordinates. So this is going to be these are going to be the bad players. The probability that f is fixed when you determine the remaining coordinates. So in other words, the remaining coordinates are the good players. So if we just look at the good players' coin flips, we'd like the output to be fixed because then we expect it to be random because they're good players. So we don't want the bad players to have any power. So, and you'll recognize this as some notion of influence. So we want to say that, again, with probability 1 minus epsilon, the function is determined by the good players, by the n minus q good players. Okay, so that's the and so for intuition, majority is resilient against close to root n bad players. The intuition here is that if there are q bad players, if the n minus q players each flip fair coins, we expect, so we expect n minus q over 2 ones and n minus q over 2 zeros, but we also expect a deviation of square root n minus q. And so if there's, so this deviation, so if the deviation is more than the number of bad players, the bad players won't be able to influence the result. So that's why majority is.
And do we care about the dependency on epsilon? Like here, epsilon is some.
Yeah, I mean, we will, but let's not. I'll discuss epsilon a bit later. And as a negative example, parity is terrible because, of course, just one bad player can see what all the other players do and choose per bit accordingly. Okay, so those are the ingredients for now. So here's a preliminary attempt. So we start with a strong seeded extractor. So we have extractors for really low entropy, so let's use it. So here, X is an NK source. So let's apply the extractor on all the different seeds. So most of the outputs will be close to uniform. Those are green, and maybe, but some of them labeled in red may be bad. Those may not be uniform. Okay, so if we have mostly good outputs, well, and the bad bits can depend on the good bits. Okay, but this is the model for resilient functions. So, yeah, right. So that's the problem. Right. So okay, so if you didn't hear Yael, you might say, well, let's just try taking the majority here. And if there aren't too many bad bits, then maybe it shouldn't be able to affect the value. But of course, as Yael said, the uniformly random bits can be arbitrarily correlated. So this is where non-malleable extractors come in. So here, I define non-malleable extractor with just one tampering function, but you could also define it for T tampering functions. And I won't redefine it, but I'll just say the corollary is that now, not only are most of the outputs uniform, but actually the good ones will be almost T-wise independent. So this seems more useful. And again, there are some really good constructions. Before I didn't have the dependency on T, basically the T adds a factor of T squared to the things. So the second attempt is to do the same thing, but use a non-malleable extractor, where where T is polylog. We'll think of T as polylog. Okay, so now, we could hope the majority can't tell the difference here, and that's actually true. Polylog will fool majority, but the issue is that there are too many bad bits. And also there's another issue that's a little more subtle. I'll explain in a second, but of course we don't expect this to be an extractor because we're only using one source, right? We have to use the other source somehow. Okay, so the subtlety is I was glossing over what it means to be almost T-wise independent. There are kind of two natural ways to think of this, and we get one, but we want the other. So in particular, we get that they're almost T-wise independent in the sense that if you look at the projection onto any T bits, these are alpha close to uniform. Right? So any T bit should be alpha close to uniform. But what we're going to end up wanting is that the distribution should be close to an exactly T-wise independent distribution. And if you do this conversion directly, you lose this factor of n to the t. Really, it's about n choose t. And so with one source, we'll never get the error to be small enough. So that's why we'll never be able to get a one source extractor. I mean, with this approach. Of course, it's impossible, we know that. But this approach can't do it because of this issue. So what we do, right, so our approach is we use X and Y to construct this, distribution so that most bits are uniform and polylog-wise independent, and then we give an explicit extractor for this. And right, so the main idea of using the second source is we'll be able to sample a pseudo-random set of indices here using the second source. So I won't go into how this works too much. So I'll just leave it there. But sampling the pseudo-random subset enables you to circumvent this issue of the error. Basically, we'll have a smaller size set, so this n to the t term will be smaller. We'll have some n prime to the t. N prime will be small enough so that this is going to be good enough. Okay, so so that's a high-level view. And for the second part, so here we're going to need this resilient function, but now, except that now it's not that the bits are uniform; they're only polylog-wise independent. So what we're going to do is we're going to build a suitable circuit that's going to correspond to a resilient function, and we're going to show that this works. But not for any resilient function. Okay, so our goal is to show that with good probability, the output of the circuit should be, the probability is not fixed should be small. Because again, if it's not fixed, then that means the good players determine the output. And the key tool here is a result by Braverman, improved quantitatively by Tal, which says that polylog-wise independence fools constant depth circuits. So if you have a polylog-wise independent distribution where the polylog depends on the depth, then the probability that the circuit outputs 1 is about the same with Z with this polylog-wise independent distribution as it is with the uniform distribution. So, the first part of our argument is to say, well, that the good bits can be assumed to be uniform and independent. And
this is because it's a polylog distribution.
right, it's polylog. Oh.
This is true if the resilient function is AC0, right?
Right, so we're going to need the resilient function to be an AC0, but we're also going to need the resilient function to be monotone, which it may not be apparent why we would need that, but you'll see in a second. The reason we're going to need monotone is that we're not interested in the probability that the circuit outputs 1 per se. We're interested in the probability that it's fixed by the good players. So we need to convert that into an AC0 circuit. So our main observation here is that if we start with an AC0 circuit, we can build another AC0 circuit that tests whether this circuit is not fixed, at least if the original circuit is monotone. So the probability that this C of X is not fixed is the probability that if it's monotone, we know that the two extremes are when the bad players are all 0 or when the bad players are all 1. So in that way, so we can just compare those two. If those are different than the bad players, then of course it's not fixed. And if those are equal, then it is fixed because it's monotone. So no matter what values the bad players put in here, it's always sandwiched between 0 and 1.
Question. I think I lost it. So why can't we use majority here? Like, wouldn't TY's independent sources have like more or less the right deviation from,
Right. So the question is, why can't we use majority? So the reason we couldn't in our original construction is that there were too many bad bits. Majority is resilient to just up to square root n. Later, Benaroya, Doron, and Tashma had a clever idea to show that actually you can use majority. And things got simpler in that way and stronger. I kind of like the resilient part, though. I was disappointed in a way. I mean, but it's a great result. But anyway, yeah, so I'll get to that. Right, so just continuing up here, right? So if C is in AC0, then the probability C prime is 1 is close to epsilon. So summing up, if the original circuit is in AC0 and monotone, the probability that C is not fixed is close to the probability it's not fixed under the uniform distribution. Okay, but now so we can assume that the good bits are independent and uniform. And so the remaining task is now we need to construct a function in AC0 that's resilient against n to the 1 minus delta bad players, because that's what the parameters of the extractors give. And it's almost unbiased. And here we could construct C in polynomial time, not necessarily AC0. We just want the output to be in AC0. So Ishan and I managed to achieve this, and Raghu Meka managed to improve the resilience using our ideas and new ideas. He matched the bound of Itai and lineal, which was non-constructive. So actually achieving resilience up to n over log squared n. So just summarizing the construction, without going into too much detail, so we start with this weak source. We apply a non-malleable extractor on all different seeds. We get this string where the good bits are polylogwise independent, and there aren't too many bad bits. The problem is that the error is too large here. So we use another source, y, to sample some bits here. We get a shorter string, and now the number of bad bits is manageable, the error is okay, and then we apply a suitable resilient function and output 0 and 1. So this is kind of an overview. Yeah. Any questions?
What is the resilient function?
Right, okay, so our resilient function, it's a way to de-randomize Itai and lineal's resilient function. So what they did was, they started with the tribes function, which is probably most of you know, it's just an OR of ands, it's just a DNF on disjoint variables. That corresponds to sort of one way of partitioning the variables. And then they showed that if you randomly partition them and get different tribes on corresponding to different partitions and take the and of those different tribes, then that's resilient with high probability. They also had to negate the variables. So their construction was non-explicit and also not monotone. And then we had a different way of, so we figured out an explicit way to do the partitions. And also we showed how to avoid the negations. So subsequently, as I mentioned, right, so Benaroya, Doron, and Tashma, their main observation was, we used a more general sampler, and they showed that if you have a sampler for small sets, that actually suffices. And then they were able to use majority And the upshot is that they were able to construct two source extractors with the same min entropy as a non-malleable extractor. And then people worked on non-malleable extractors. And again, the best result is this result by Shinley, building on previous works by Ishan and Gil Cohen. And the main tool here is alternating extraction, which I won't go into. Okay, so now I want to talk about, question.
On the previous slide, so was resilience not a model? It was not a bottleneck for your construction, and not a bottleneck for them. So they could just use a majority function. Is that right?
Right. So at this point, the bottleneck is just improving the non-malleable extractor. We're pretty close to optimal. The optimal is log n. I mean, to get the two source extractor.
Zero is sort of even sort of beside the point, right? That's only because you can apply Randomness and sort of reduce to a similar problem without the CYs. Really, the question is, you don't have capacity of the resilient function as long as it can handle device independent.
Right, as long as it handles two. Well, right. Well, we also need a way. So again, it's not sufficient just that the Ty is independent fools it, but we need this. We used monotonicity to test. Right, so we used monotonicity to say that right, what we want to fool is the probability that the bad players can influence the result. And there we use monotonicity, and I don't know how to avoid that per se. But maybe there's some way to do that. Okay, so now let's talk about the error bottleneck. So as I mentioned earlier, this framework can only achieve polynomial error. And the bottleneck is the resilient function. In particular, the isoparametric theorem implies that the error will always be 1 over m. Here, m is the number of bits, it's the length of the string that we apply the resilient function to. Think of m as n. So, Konkali linear showed that the error is actually log m over m, but that's really beside the point. The error is at least 1 over polynomial. So one cool way to circumvent this for certain tasks is to get a low error condenser. So here instead of aiming to output a bit or bits that are uniform, Benaloya, Cohen, Doron, and Tashma said, let's just try to output a high entropy string. And here we can hope that the error is quite small. And as Evgeny mentioned, this suffices for what he called unpredictability tasks. So for K, so what they showed is that if K is polylog n, they're able to output an n-bit string Z so that the mean entropy of this is at least m minus a small constant. Here, epsilon this notation means that it's not this distribution that has min entropy, but this distribution is epsilon close to a distribution with min entropy m minus little o of log 1 over epsilon. Okay, but now notice that there's a log here, log 1 over epsilon. So now we can have epsilon be negligible, and the output is very close to uniform. And their construction idea is similar to what we've seen. They're going to start with the approach that we did, and then they're going to, at some point, they're going to chop the. So this is the string Z1 through Zm is the output before applying the resilient function, and here I chopped it into blocks. So each Zi has some length r, say. And then they apply a resilient function to each of these blocks. And they show that this is a good condenser. Okay. And as a cool corollary, now that they can immediately get a 3-source extractor where the third source needs just a small number of random bits. Sorry, a small amount of min entropy, just constant times log 1 over epsilon. It doesn't even depend on n here. Okay, so that's one cool thing that, and this has been used in a couple of results. So let me tell you, here's some work that, so Kumar Mecca and Sahai introduced sources that are correlated by communication. And they have cryptographic motivation. So here, so this is about communication complexity. I won't go over the model, probably most of you know it. So imagine communication complexity with more than 2 players. The standard model here is usually the number on forehead model, where you think of having your input on your forehead, everyone else can see it, but you can't. In other words, every string communicated can depend on all but one of the inputs. The number in hand model, which may be more natural, just says each string depends on one input. So viewed in this way, it's very natural to define what they did, the bounded collusion model, where each string just depends on p inputs. And they gave some, this lower bound follows from number on forehead, and they defined these extractors for BCP leakage. But actually, the main result really was an application to leakage resilient secret sharing. So I want to, so in some joint work with a bunch of people, we have some improved results along these lines. So one thing is a lower bound in communication complexity. Here we were, if only 0.99 R players can communicate at a time, then we give an explicit function that has communication complexity at least polynomial in n. So of course the number on forehead model has a bottleneck at log n. So this is kind of interesting that we could beat it. Extractors with min entropy actually everything. So where you even start with uniform strings, give average case lower bounds. But we can give an explicit construction where the min entropy is actually tiny, just polylog n, where we allow some leakage from these bounded collusion protocols, where the protocol is about 0.99 R. And using this, we can get efficient T out of R secret sharing, leakage resilience against bounded collusion protocols, where we allow complete leakage of any T-1 shares. So that's what what's usually in threshold secret sharing. But we also allow this leakage in the bounded collusion model, where P is in most R over log R.
Scales predominantly the number of players, or that some exponential
Sorry, say that again.
So everything here scales polynomially with T. R.
Yeah, I think that's right.
I'm not sure I quite got the leakage model here. So, like I understand, each input depends on the other. So,
Right.
or
So
each output, sorry, depends on the inputs.
right. So think of you write. Right. So you have players writing on the board. Right. So at any moment, you could have P players. You could have P players get together. Look at their inputs and write some function of their inputs as well as what was previously written on the blackboard, and they can write that they can add that to the blackboard.
And this goes in.
And this can go for a polynomial number of rounds.
And you want the output of the extractor to be uniform, give this information.
Right.
Bounded communication, right? So to that, you would have some entropy left for sure.
Right.
what's the number?
Yeah, right.
Rounds? I get like somehow I was confused by the
Wait, wait,
round was stated.
Yeah, wait, so, yeah, wait, now next.
Fully understand the statement.
Right, so-
The alpha leakage from BC.
Right, so sorry, so I said polynomial, but in other words, the number of bits that are written on the blackboard is the most key, k to the alpha, sorry.
So think of it as like for k over k to the alpha rounds.
Yeah.
A group of people, people get together, write a bit.
Yeah. Yeah, that's a better way to say it, right. Right, so k to the alpha rounds, and each round, p players get together, write a bit that depend on their inputs, and what was previously written on the blackboard.
And here k is the min entropy again.
Right.
Next.
Oh, yeah, so, yeah, just a few words about, what went into this. I guess I'm almost done. Let's see, so the lower bound was proved for, you could take the most significant bit of the product of x1 through xr, where you work in some field, f2 to the n. And so average case lower bounds correspond to extractors for high entropy. And the main point is that, bringing up what we did before is, if we want an extractor for low entropy, we can apply the condenser that we just discussed. So here, the inputs are x1 through xr. We're going to sacrifice one of the x's, say xr. We're going to set yi equal to the condenser of xi and xr. So now we have r minus one of the yi's, and now we'll do this, this function here, applied to y1 through yr minus one. Although we'll output, instead of the one most significant bit, we'll output, say, m of the most significant bits. And then, so basically for most fixings of this one string xr, the output of yi has high entropy, and this enables us to use these average case lower bounds. So it's basically a reduction using this two-source condenser. Another cool use of the two-source condenser is in this adversarial source model by Chattopadhyay, Goodman, Goyal, and Lee. Here they have R independent sources, S of which have min entropy K. So it's a very natural model. And Chattopadhyay and Goodman gave an improvement, and just as an upshot, they said that they obtain extractors if the number of good sources is R to some power, and K is polylog n. So it's a natural model. And curiously, they use the extractors for the leakage that we just discussed. And actually, the main motivation for them was to build improved extractors for small space sources, which I didn't define, but it's an interesting model. Okay, so there are a whole bunch of other crypto-related extractors that I didn't have time to talk about, but I hope I gave you a sense that there's really a lot here. So many types of extractors have cryptographic applications. It's natural to ask if we can find even more connections. And I hope you came across that different types of extractors are related in non-obvious ways. I mean, this talk we used non-malleable extractors to build two-source extractors, and we used those. And then there were two-source condensers, and those went into building these extractors for BCP leakage, and those went into building extractors for adversarial sources. So it's really a lot of different connections. Some open questions about two-source extractors. I think most relevant for crypto is to get negligible error. Mark Luco achieved k bigger than 4/9 n using Bourgain type methods, I guess. But there's a long way to go. It's not explicitly we can achieve just any any function that grows faster than log n, since the error is non-explicitly, the error is like n over 2 to the k. And can we get the min entropy down to order log n? So that would be, we're almost there, but this would be nice because then it would give polylog n Ramsey graphs, if you know what those are. And of course, even 1 times log n is the ultimate goal, because then you get order log n Ramsey graphs, which explicitly answers a question by Erdős. And another question is to simplify the construction. And even more generally, can we have other tools to beat the expander and mixing lemma for small sets? So this was, this is one specific function, but it'd be very interesting, I think, to say more generally, there's some sort of, if you have some graph that satisfies maybe some other conditions, we can have something even stronger than the expander mixing lemma. So I think that's it.
We've got time for questions. There's a Mohammed beach to it. There's a question on Zoom. There's a question on Zoom. David, I don't know if you can read it.
Okay. Thanks.
Yeah, Mohammed, if you want to unmute and just ask the question out loud.
Sure, I'm muted. Do you hear me?
Yes.
Yeah, so earlier in the talk, you mentioned network extractors. It was kind of like MPC model where you mentioned that you can even allow Byzantine corruption. Does that sound like much more general than the adversarial extractors mentioned towards the end of the talk, where you only assume a fixed number of the sources to have mean entropy, but not the rest of them? It just sounded more general, so I wondered if there is like a subtle reason that we need adversarial extractors, or do they not fall into network extractors?
Right. I mean, the parameters for the adversarial extractors are better in the sense you only need a few of the sources to be good.
But the model falls into that one as well. Got it.
Oh, the model, right. Yeah, I mean, if we could build, right, I guess if we could build network extractor protocols with the same parameters, but we don't know how to do that.
I see.
But I think you're right that it's, yeah, that the model, with the same parameters, I think you're right that, yeah, that network extractor protocols is a more challenging model. It's just that we can't do the same parameters.
Got it. Thank you.
So, yeah.
Yeah, there's only one mic.
Oh, sorry. So, yeah, my question is about being explicit. So, you guys really want explicit extractors because, so in crypto, we also want explicit constructions, but not for the same reason. So I guess the question, when you say non-explicit, usually you say, oh, there's an existential result using various algorithms. But for us, we just want an efficient. So as long as you have an efficient construction, let's say, extractor, even though it's not explicit in the sense that maybe you assume some non-uniform advice that who knows how you got it. For us, as a cryptographers, often it's good enough because once to generate this random thing, we can manage to do it. So all we want is like a non-explicit but efficient construction. I feel like in complexity, well, randomized, you need to be careful, right? Because you don't have randomness. But yes, randomized once and for all. So one rand once and for all that should fool all possible weak.
Right.
Well, it should fool every possible source. That's the point.
Yeah, right.
And-
You're saying like a probabilistic method.
Efficient.
If it has sufficient,
Yes. So my question is, was this was this study that type of, or do you think it also makes things much easier? But again, the focus on efficient construction, so not probabilistic methods.
Explicit version of this, suppose that we see each of the polynomial in any seats determines the random linear function, chosen independently and random. We know how to analyze this today. I asked this question 20 years ago. The answer was that we don't know how to analyze it. So today we know how to analyze this as well.
Okay, so let's start with, yeah, Elle's question. So the leftover hash lemma itself, that already extracts from any source.
If you want logarithmic
But-
seat size, we have
but
polynomial
right, so-
seats. Yeah, every seat.
Okay, right. So you're asking about, yeah, so I don't think we know how to we don't know how to analyze random linear extractors with a small number of seeds. Yeah, I think that's a great question. And you're saying that would be interesting for crypto.
That's semi-explicit in the sense of the question.
Yes.
Right, although,
And
right,
the factor is that it's a semi-explicit construction in the sense of the
right. Right, I guess if you allowed 2 to the n linear functions, we would know it because of the leftover hash lemma, so that's efficient, but you're asking sort of, we want something a bit better, and we don't know how to do that. As far as, or do, well, 2-source extract, oh, Will it-
Construct two-source extractor and that's aware, but as long as that the construction is not explicit, but it should be efficient. Once you determine that non-explicit part, it should be efficient.
I see, so you're saying for most choices of this?
What do we know about that? The great degree of two-source extractors is a bit better than linear code that was.
Right, so the algebraic, well, so Mark Luco had that 4-9-sen, which was an algebraic construction, and that's, right, I don't know of any results along those lines. Yeah, but we should, yeah, maybe we should look at these questions more complexity.
Other questions? Ben, you have a question? It's related.
So I was wondering about like a ZPP construction. It's similar to Yael's question, like say that I'm willing to use randomness for free. It should be polynomial time, but I want a 0 error. Maybe I want to be able to detect the event that the selected construction was bad, for example. So, right. So I think that for expanders, actually beyond the mixing lemma, we don't know how to do it. But I don't know, maybe for extractors it's easier. So
Yeah, so that's another great question. Yeah, I think we don't know the answer. So if, like, let's say we want to generate another, yeah, we want to use randomness to generate a graph but we want a certificate that has good extraction properties, say 2-source extraction properties. Yeah, we don't know how to do that. I don't. Right, with expanders, at least we know eigenvalues. We can at least check that, and that gives something. Whereas, yeah, for random graphs, yeah, I don't even know how to beat just the eigenvalue bound of n/2. Yeah. So, any other questions?
Probably stop
Oh,
here
okay.
because we're already quite a bit over time. But let's thank David again.